Now that we know how to find velocity at any given point, we can do it at many different points. Here I've drawn tangents to times 1 second, 2 seconds, and 4 seconds on this graph. So here is our graph, and we have 1 second, 2 seconds, and 4 second tangent lines. The important thing to notice here is these lines are not parallel. But they're not parallel, so they have different slopes, implying the object has had a different velocity at each of those moments. It isn't probably a shock to you that something can have different velocities at different times. We quantify that by considering the rate at which the velocity changes, something called acceleration. Acceleration is defined analogously to velocity. For example, the average acceleration between the start and end of an interval is found by a sub average is delta v over delta t. Right? It's the change in velocity over the duration of the motion. Since velocity is measured in meters per second and time is measured in seconds, we see that acceleration is measured in meters per second, meters per second over second, which is read as meters per second per second. But because that's incredibly awkward to write or to say, we usually perform an algebraic trick, and we say meters per second algebraically would be take the first one and do keep flip change. So we keep the first one, we flip the sense, which is that we change to 1 over seconds, right? Seconds becomes 1 over seconds, multiply. And then algebraically, the m times 1 becomes just m, and the s times s becomes s squared, because anything times itself is a square. And so we read this as meters per second squared. We're not really squaring the seconds. This is not it's not easy to think of this as sort of a meters over some squared quantity of time. It's just an algebraic convenience, but it's a universal one, and we'll use it consistently. As an example, a given sports car has a 0 to 60 time of 2.7 seconds. What is its acceleration in meters per second squared? And in case you don't know, the 0 to 60 time is how long does it take a car starting from rest to reach a speed of 60 miles an hour. Then we'll follow on with a different question. If a different car had a 0 to 60 time of 3.3 seconds, would its acceleration be higher than the first car or lower, and how do you know? The first part's easy. A sub average is delta v over delta t, so we ended at 60 miles per hour after 2.7 seconds, and we start at 0 miles per hour at 0 seconds. Then we have to do some grunchy conversions. So 60 miles per hour times 1.6 kilometers per mile, that, as we've done a couple times now, lets us get rid of the miles. And 1,000 meters per kilometer gets rid of the kilometers. And 1 hour turns out to be 3,600 seconds, so we get rid of the hours. And we're left with meters per second, that's what we wanted, divided by seconds. This all turns out to be, if you grind it out, 9.876 meters per second squared, which we should round for sig figs to 9.9 meters per second squared. As an aside, I've assumed the 60 is actually 60. In other words, would be distinct from 59 or 61, even though our usual rules would say if you had a 60, we should treat that as 1 sig fig. But nobody in their right mind writes 60 miles an hour correctly to say this, which is what you should write if you wanted to have 2 sig figs. All right. Nobody does that, and so I'm just going to play a little fast and loose with those rules, but keep in mind, if we had to follow that, then we'd say this was really 10. For part B, since the time is longer, the denominator is bigger, which means that the whole fraction is smaller, the acceleration is less. The following drawings represent strobe photographs of a ball moving in the direction of the arrow. The circles represent the positions of the ball at succeeding instants of time. Time interval between successive positions is the same in all cases, and assume that all accelerations are constant. Draw a blue circle around the case or cases with the acceleration with greatest magnitude, and a red circle around the case or cases with the acceleration with the least magnitude. So the least turns out to be really easy, because if we look over here, in case A and B and D, the distance between flashes changes, and therefore the velocity changes, and because remember that would be approximately that distance divided by the flash rate, or flash time. But in case C, it doesn't. It travels the same distance per flash, so the delta x is in any given delta t is the same. The velocity is always the same. It doesn't change. This has a magnitude of 0 meters per second square. And 0 is the least you can have for something for magnitudes. All right, then it gets a little trickier. Which of these should we do for the others? Well, A, B, and D have the similar kinds of motion, And here we're going to play, you could either say if those lines are equal, because there's no scale easily drawn, if those lines are equal, then the accelerations would be equal, at least in magnitude. But if we take the directions as actual Cartesian directions, then we can see that this is the longest line, so these are greater intervals than this. So the acceleration would be larger. That's a bit flaky and shifty even, so I wouldn't sweat too much over it, but they might all be the same if those distances are the same, or if we treat the geometry the way it looks like D would have the greatest. As with velocity, we can talk about the instantaneous acceleration, that is the acceleration at a specific moment in time, as the limit of the average acceleration. That is, A is the limit as the time interval becomes small of the ratio of the change in speed to the change in time. But again, this requires calculus to go further. It's useful to think of instantaneous acceleration as an average acceleration measured over a very short time interval. If the velocity is not constant, then it changes. It's sort of duh. That means we could make a plot of the velocity as a function of time, a so-called velocity plot or VT plot, and on that kind of plot, the acceleration can be found as the slope of the tangent line on VT plots. That is to say, the acceleration is to the velocity as the velocity is to the position. It plays the same role, just one step further down. All right. The graphs below show the velocity versus time for boats traveling along a straight, narrow channel. The scales on both time axes are the same for all of these graphs. In each graph, a point is marked with a dot. Draw a blue circle around the cases with the acceleration with the greatest magnitude at that moment, and a red circle around the cases with the least acceleration in magnitude. We're going to deploy a couple of tricks here. The acceleration is the slope of the velocity plot, and we can see already that, for instance, this line and this line are parallel. So A and B are the same. I don't know if they're the most or least, but they're definitely the same. Likewise, C and D have the same. They're parallel. You can see that here. And then a last little trick, if we look here, E increases by 1 unit over the whole 6, while F decreases by 1 unit over the whole 6. And so their slopes, while not equal, are negatives of each other. So in absolute value, they're equal. So really, A and B are linked, C and D are linked, E and F are linked. Now we just want to compare those. So if we look and we say, well, clearly E is shallower than everybody else, so E and F are going to be the least. And a little more, takes a little bit more work, but this changes by going up 3 in 6 units, whereas C goes down 4 in only 3 units. So C is steeper than A, and C and D therefore are then the ones with the greatest acceleration. In magnitude, it has a negative acceleration, but we'll strip that to get the magnitude. Some really important linguistic things, at least for English. The idea of speeding up or slowing down. I really don't like speeding up or slowing down. I'll try and say gaining speed or losing speed, because the up and down kind of immediately make you think about, well, up and down, sort of duh. And that can get us into trouble when we have things that actually move up and down. But speeding up, which is the same as gaining speed or getting faster, means the speed increases. The speed increases, not necessarily the velocity. That means that, for instance, if I have something which is going has an initial speed of minus 2 meters per second, and then has a later speed of minus 5 meters per second, the acceleration would be negative, minus 5 minus 2, which is minus 3 over the time interval. But the object is clearly getting faster. It was going at 2 meters per second, now it's going at 5 meters per second. So even though the velocity has become less, because minus 5 is less than minus 2, the object is going faster, because 5 is more than 2. This ends up boiling down to these very important little things. If V and A point in the same direction, then the object gains speed. And if V and A point in opposite directions, then the object loses speed. It's a bidirectional, so if an object is losing speed, we know the velocity and the acceleration are oppositely directed. Right? This is something which is relatively easy, but a little subtle and really useful in the AP context. They really ask questions a lot of times that hinge on this. So it's worth kind of committing to memory that if the two are aligned, you get faster, and if they're counter to each other, you get slower. Carmela and Desi leave their physics classroom separately and travel west. They both start from rest. Desi left first, traveling with an acceleration of 4 meters per second squared for the first 6 seconds, and then he traveled at constant velocity. 2 seconds after Desi started, Carmela began with an acceleration of 3 meters per second squared for 10 seconds, and after that, she traveled at constant velocity. Graph the velocity of both travelers as a function of time up to 16 seconds, starting at t equals 0 when Desi leaves the classroom. Use a blue line for Desi and a red line for Carmela. So let's do that. If he travels 4 meters per second squared for 6 seconds, then at 6 seconds he'll have a velocity of 24. So something like that, and then constant. And for Carmela, we're going to do something similar, that after her 10 seconds of travel, she'll have a speed of 30, but it starts at 2 seconds. So at 2 seconds, she's 0, and at 12 seconds, she's at 30. So that, something like that, would come out. All right, if the vertical axis of this graph is position, at what time does the object change direction? Well, if this is a position curve, if this is x, then the slope is the velocity, but a line has a constant slope. So the velocity doesn't change. So -1. If the vertical axis is velocity, at what time does the object change direction? So now we're saying this is v. Well, an object can change direction when it goes from either moving positive to moving negative, or when it says from moving negative to moving positive. But that has to be a change in velocity, and on this graph we can read the velocity. So for times less than 4 seconds, the velocity is negative. And for times more than 4 seconds, the velocity is positive. So the switch has to occur at 4 seconds.